Thank you everybody for showing up at 8 a.m. I'm going to go over essentially 4 areas in this talk. Give you a brief description about what a memristor is. Who has heard of memristor? Almost everybody, great, okay. Brief history that you might not be aware of. Brief review of what disruption is, since this is a disruptive technology conference, and how memristors are poised for disruption. I'll then talk about memristor synapses, which I think is one of the more disruptive applications. And then an overview of what it is we're working on at Knowm. Memristors are, it's a variable resistor. Like, instead of having like a knob that you tune, think of it as a black box, lots of physics, different for every memristor that changes the resistance as a function of how it's used. It can be voltage controlled, current controlled. There's lots of memristors out there. It's a much bigger field than people realize. If you'd like a mathematical formalism from the inventor himself, you can read his papers. He has a whole theory for going from ideal memristors all the way up to what he calls extended memristors. Think about them as state-dependent resistors, and the state is changed on how they're used, and it's a function of the physics. And so it encompasses a very, very wide range of resistive changing materials. ReRAM is included in that. Anything that changes its resistance as a function of its prior history, any two-terminal device. So Leon Chua formalized this in 1971. In 1970 is sort of the first modern publication of a resistance-changing device coming from Dernley. This is an oxide-based device. So this is the year before memristors were theoretically invented. In 2000, Mitkova, this was the precursor to some of the devices that we work with at Knowm. This is the silver chalcogenide-based devices. This goes back actually quite a ways. If you go outside of peer-reviewed literature, a man named STEINER measured the electrical properties of the black crud that he found on some cartridges in an arroyo on a hike behind his house. So this has been around for a while. I came on the scene in 2002. I was looking for a mechanism for creating a device, physical device that worked more like a synapse. I had no idea the word memristor even existed at the time. And I thought about the dielectrophoretic aggregation of nanoparticles. Anyway, I looked around literature. There was tons of supporting evidence that something like that was possible. That ultimately led to the creation of the Synapse program in 2008. You can see the particle synapse up there. And then another pivotal moment in the history of memristors occurred in 2008. So this is a plot of the citations and patents per year for memristor. And you can see there's this inflection point at 2008. That's when HP announced their discovery of the missing memristor. Notice all the examples I gave you predate 2002. So they didn't actually come up with it, but they did unify everybody around a common name. Up until then, most people didn't know that there was a formalism for it, that the word memristor even existed, that there was somebody named Leon Chua that did it. After that, it's been taking off. In 2018, we can expect about 3,000 citations, patents combined. Because this is a disruptive technologies conference, a review about what disruption is. Technology is not intrinsically disruptive. Disruption implies how a business enters a new market. I didn't realize this until I was invited to a disruptive technologies conference in California. I started looking into it. There's 2 types of disruption. There's new market disruption. That's what happens when a technology enables new products and new services that didn't exist before. That's really kind of exciting disruption. And then there's low-end disruption, which is often when a new technology, sometimes just a different business model, enables a new player to come in and compete with incumbents at the low end of the scale, bottom-tier clients, and then get a foothold and then sort of work their way up until they can take over a market. That's probably what most people talk about. The more exciting one is the new market disruption. So memristors, as far as new market disruption, memristors themselves, you saw that plot of the interest in memristors, going up every year. It's accelerating, and oddly enough, nobody was selling them. So we decided to offer memristors to the research community. It's easy to make a memristor. It's very hard to make a good memristor. We license technology from Boise State University, a silver cacogenide-based device, inventor Dr. Chris Campbell. We've sold discrete memristors, and we're moving into crossbars and various synaptic arrays and whatnot to clients in about 30 countries so far. So interest is global. We're shipping these things all over the world. People are finally getting their hands on them, mostly circuit developers trying to understand how to make devices, make circuits. And then there sort of offers some low-end disruption tooling, mostly for measurement. And this is actually the first industry that's going to be disrupted by memristors, is the electronic design automation. There's this growing interest of people around the world, and the semiconductor industry has consolidated year after year. If you've ever worked in this field, you know that anything having to do with this industry is obnoxiously expensive. The go-to piece of equipment that Dr. Campbell, who invented this device, that she uses, this B1500 over here, starting price is $50,000. To take a fairly accurate measurement of a memristor's conductance is actually not trivial. You got to control the current. It's not easy. One of our collaborators in Chile took our sort of USB platform, hacked together a circuit, and is taking measurements on par with this instrument for about $200. So the incumbent tooling is both inadequate and way too expensive. And so people are cobbling together open source tools in order to bridge the stack. It's something that we've done. So from circuit simulation all the way to VLSI layout, there's now open source tools available to actually design your circuits, model them, layout, verification, all of that. So this is really going to be, I think, the first major industry to be disrupted. In terms of applications, I want to make two important points. Memristors are billed as this fundamental new passive circuit element. That's what Leon Shua described. And it's true. And if you think about it like that, if you only had a few basic circuit elements to begin with, and then you add another one, it fundamentally changes electronics. So you go back and you review all the previous circuits that have been devised, and you realize there's different ways to go about it. And so there's this potential of massive disruption. On the other hand, if you're designing a circuit based on ideal equations for memristor, I promise you it's not going to work whenever you actually get your hand on a real one, because there's a laundry list of real-world properties that will hang you up. And the way people design for modern digital electronics and the way the memristors want to be used is not really the same. Things like fabrication yield, switching speed, endurance, deterministic behavior, all of this stuff will probably throw a wrench in your parade if you don't take it into account. So ideal memristors don't exist. There's a lot of things you have to deal with. You need to get your hands on actual devices, measure them, make sure that your idea is going to work with what actually exists. In terms of the major areas of applications, there's sort of reconfigurable logic and memory. That's more of the traditional space. There would be an opportunity for low-end disruption, but that's sort of the incumbent's playing field right now. And there's a lot of risk aversion. New fabs don't want to introduce memristors, especially if there's exotic materials as part of the process. That's a biggie. The fabrication yield, designing when you don't have 99.999% yield is difficult. A lot of the way that we do things is sort of based on transistors, and this whole industry, memristors don't fit in. On the other hand, there's this new area, synapses, AI, and that's probably the biggest opportunity for disruption that I can see. The scale of the ongoing AI disruption is phenomenal, and it's hard to get across just how big this thing is. We're just in the beginnings of it. But to try to give you a sense of it, the transistor is humanity's biggest invention, by far, most successful invention. We produce about 7.9 trillion per second globally. But if you imagine a future where we've worked out most of the basics of artificial intelligence. We've matched human performance across a number of disciplines, and we figured out how to map that to ultra-efficient hardware that can perform at the level of biology. Then you ask yourself, what markets are possible? The total amount of synapses produced by honeybees every year exceeds the amount of transistors that humanity produces every year. The total, say, automation market for humans, that's 5 quadrillion synapses per second every year. The scale of what would be possible in a future where we have ubiquitous, high-performance machine learning hardware on par with biological systems is absolutely immense. In the best case, it's societal level transformation, disruption of like every industry. And in the worst case, it's human extinction. So we won't say where on that scale we're going to fall. It is going to be a massive disruption, and it's currently ongoing. And memristors don't currently play a role in it, but they will. What we work on, we call it AHaH computing, ANTI-HEBBIAN and Hebbian computing. There's sort of a long history to this, but suffice it to say it's about doing machine learning-centric computing, taking into consideration the constraints of implementation in ultra-efficient memristive hardware. Not necessarily even memristive, just trying to reduce the energy of synaptic operations, which ultimately amount to communication. Modern systems, modern digital computing methods are horrible at synaptic electronics because they separate memory and processing. That's sort of a fundamental tenet of modern computing. Communication between memory and processing is a horrifically bad idea when it comes to synaptic processing. So you have to reduce the precision of your synapses or go analog. You have to have a sparsity of activation. You don't want to communicate any more than you need to. You want locality. You want to keep all the computation as close to where the memory is as possible, and you want to lower the voltage as much as possible. So what we do is machine learning under those constraints. We work with something we call thermodynamic RAM, or KT-RAM for short. It's this AHaH node computing resource. Don't think of this as a whole neuromorphic processor. Think of it as SRAM is to a processor as KT-RAM is to a synaptic processor. It's the thing that does the synaptic integration and learning. We work with spike sets for data representations. So most machine learning uses dense floating point vectors. We use sparse integer collections to represent information. We do that. It's very efficient to communicate. It also gives you interesting things like the spikes directly index synapses. Then you can execute these instructions, and you can get various types of learning from them. There's various types of cores, various ways to array these synapses, which are formed from differential pairs of memristors. You can see the variations, some of them down there. We use primarily developed on the non-topologically constrained, the one with the red boxes there. If you go out into the literature or go to conferences, you'll find that we all have different names for this, but everybody's converging on effectively the same ideas. Differential pair memristors for synapses, lots of exploration of crossbar structures. Some people are moving away from that. Needless to say, there's lots of groups out there. This is sort of a snapshot, and we're all kind of going in towards the same area. We've taken this idea of thermodynamic RAM, built emulators on top of it, won't get into the complexity involved in that, and started to search the space for machine learning functions. What can we do that we can map to what we call AHaH routines, these set of routines that execute these basic instructions on differential pair memristor synapses. And very rapidly we discovered quite a lot of machine learning, and we got hung up on supervised deep learning for a while, and we finally sort of found a way in there. So at this point we can do pretty much everything from basic logic on up to unsupervised and supervised machine learning. Now before I conclude, I'd like to point out there's an opportunity for a new market disruption, for a market that's just being created. So deep learning has sort of come on the scene, and it's enabled basically vision systems that finally work. And there's a fundamental flaw in deep learning vision systems. And it's that they can be spoofed by adversarial images. This is, at first it was thought this was just sort of an academic thing, that you could, maybe just tilt the image or just introduce, just slight variations and then this problem would go away, but it turns out it's a little more robust than that. There's these sort of abstract images you see up here at the top right, that sort of look like wallpaper. They've been evolved to elicit a high confidence prediction for some class. So you can sort of see that, like baseball, it kind of has the elements of the baseball, but it just looks like wallpaper for the most part. Well, we were sort of starting up this new program because we discovered we could do anomaly detection, and we thought, well, wait a minute, what if you had camouflage? You could have sort of deep neural network camouflage. Like a month after that, a group demonstrated this adversarial perturbed turtle. Has anybody seen this? So they took a 3D printed turtle and they put basically a special camouflage. So from every angle, the neural network says it's a rifle instead of a turtle. So it's in the real world. This isn't something that's just one image from one orientation or whatever. It's robust to all the transformations. So it's possible to evolve a camouflage that will radically alter the performance of a deep neural network. And the reason is that error gradient methods for classification are fundamentally incompatible with anomaly detection. Making a discrimination is not the same thing as outlier detection. Right, so imagine you're trying to tell the difference between dogs and cats. A deep neural network will say, that's a cat. Absolutely, that's a cat. End of story. But that's not necessarily what you want. You want to say, that's a cat. That is a really weird cat. Take a look at this. So there's this sort of fundamental problem with deep networks having to do with anomaly detection. We actually stumbled upon a solution to this with AHaH computing. We have this whole set of hardware constraints and data representation that's different, and it's based on the hardware. And we noticed that anomaly detection popped out of this framework essentially for free. General anomaly detection, including vision. So we actually demoed this on something we call InSpec, which was developed for counterfeit detections in chips. So you can give it all the normal, everything that you say is normal. It'll learn what's there, and then it'll tell you what the anomaly is if there's differences. So it's capable of telling you that there's something wrong because it's building up a statistical model, a distribution of the underlying space. This is part of an ongoing phase 3 SPIR with AFRL Rome in New York. As part of this, we figured out also how to extract deep neural networks and move them into our framework and to get anomaly detection in the process. And we've built this all on top of our emulators that map back to Memristors. So to wrap this up, Memristors they're more general and they're far more complicated than most people realize. They're not just the idealized elements, those don't exist. The truth is that they're very complicated, and where that fantasy meets fact is where you need to be. You need to get your hands on actual devices if you want to design for Memristors. They've been around a lot longer than you might think, since before people even formalized that they should exist, and they're a lot harder to understand than you may realize. Synapses, I believe, are the most disruptive Memristor application because their properties actually, building synaptic processors matches better with the actual physical properties of Memristors than some of the non-ideal properties. The disruption, the scale of that is going to be massive, and the first industry that's going to be disrupted is going to be all the tool chains having to do with using Memristors, all the electronic design automation software. Special thanks to AFRL Rome. They funded our work over a number of years to get to the point where we can start demonstrating useful machine learning with neuromemristive systems. With that, I can take questions, or if I'm out of time, maybe sit down.
Well, thank you sir, for an excellent talk. We have time for one short question, if anybody would like to ask something.
One of my big things is, I had lunch with Leon Chua.
Oh, okay.
The crosstalk.
In an array.
If it's too close, there is these
Mhm.
sync function effects, if you ask me. Well, what have you done to mitigate things like that?
With
When
the
you start
cross.
flowing electricity in these MEMRISTOR circuits, according to some guy, some researcher,
Mhm.
there was a lot of ineffect, just like co-channel.
Totally, yeah. That's a problem with crossbars. So not all architectures use crossbars. The version of KTRAM we're developing actually doesn't, specifically to eliminate issues like that. Depending upon how you drive the circuit, you get it. If you use sparse representations, you'll get it because some of the internal wires will be floating. Some groups have mitigated it by using an array of smaller crossbars. Some applications actually utilize that kind of thing. So puffs, physically unquotable functions, they like that kind of stuff. My point is exactly to this effect, which is you have to understand all these non-ideal things. People will develop an idea sort of in this fantasy using idealized equations, and they'll sweep all that under the rug, and then they go to implement it, if they can even get the memristors to implement it, and they realize, oh, this isn't going to work. That's just one of the issues. You get to learning circuits, and you start having non-ideal incrementation, non-symmetrical stuff. It goes on and on and on. It's a very complicated field, and you have to design with all of that into consideration. And it has to be captured in your EDA software. Typical digital synthesis and all that isn't necessarily going to work.
Okay, well, let's thank the speaker one last time.